Okay, so this problem has us estimating sine of 13/12 pi using a Taylor polynomial about x equals pi. It asks us what the least degree is of polynomial that assures an error smaller than 0.001. So a key wording here is least degree of polynomial. Occasionally we'll get mistaken and we'll start using our n value for a term when we really are asking for a degree, and it can be easy to confuse that because the term number doesn't always match perfectly with the degree depending on the particular Taylor polynomial we're looking at. So first thing I want to do is I want to take a look at the parent function, which is sine x, and I'm going to run through a handful of derivatives to see if we can come up with a pattern. So f prime of x equals cosine x, f double prime of x equals negative sine x, f triple prime of x equals negative cosine x, and then that's going to repeat as I go, so we're going to be back to a sine x, cosine x, negative sine x, negative cosine x. Now, we're curious about x equals pi, so my sine values are going to be 0 at pi. Cosine is going to start at -1, then back to a 0, to a +1, 0, -1, 0, +1, and then that pattern will keep going. So if I want to build a polynomial, we'll just call it p sub n of x equals, we're going to start with the first derivative, which is 0, over 0 factorial. Alright, then we're going to take the next one, so minus, and this time we've got a 1 over 1 factorial, times x minus the center to the first. Alright, then we're going to have our next term, which is plus a 0 over 2 factorial, times x minus pi to the second. Then we're going to have the next term, which is a 1, so plus 1 over 3 factorial, x minus pi to the third. And we're going to keep going with that. Now, hopefully at this point you're noticing that this starts with a negative, and we have 1 over 1 factorial times x minus pi. Then we have 1 over 3 factorial times x minus pi to the third. And it looks like we're getting the opposite of what sine is, and then we're adjusted for another center. If you remember a trig identity, sine of x minus pi, that's going to actually equal the negative sine x, and that's why we're getting that opposite sign. You can expand this using our identity if you want to kind of verify that. So I've got p sub n of x equals, and we're going to be negative 1 times x minus pi, alright, 0 term disappears, 0 term disappears, plus 1 over 3 factorial, x minus pi to the third. Alright, then a 0 term is going to cancel, and then we're going to be back to a minus, and we're going to have 1 over 5 factorial, x minus pi to the fifth. Now, this is going to keep going, and we're going to get negative 1, and we started with negative, so I'm going to put this as an n, where n stands for the term number. So that would make the first term negative, the second term positive, and so on. Alright, then we're going to have that over n factorial. We actually can't do n factorial there because we chose n to be the place in line. So I'm going to have to take a 2n minus 1. That way when I plug 1 in, I get 1, first place in line. When I plug 2 in, I get 3, and that's for our second place in line. There's a 3 factorial at the bottom. Alright, now I'm going to multiply that by x minus pi to the 2n minus 1 as well, because that's going to match up. So when I'm on the first term, I have an exponent of 1. When I'm on the second term, I have an exponent of 3, and so on all the way down. Now, one thing that I noticed straight out of the gates is this is an alternating series, and when we have an alternating series, we get by with the alternating series error bound. This allows us to not worry about trying to find the maximum value that the n+1 derivative reaches over a certain interval. We can just use the center for finding that value. So now, to start working with this, I'm going to pull this over here, and I'm going to focus in on the n+1 term. Alright, so I have an absolute value on it because we're just curious about the magnitude. So I have negative 1 to the n+1 times x minus pi, But in our particular case, that x is going to be 13 over 12 pi. So we have that minus pi to the 2n plus 1, and the n plus 1 in parentheses minus 1. So that's going to end up being a 2n plus 1 overall. And then that same thing's going to happen in the bottom, where we're going to have a 2n plus 1 factorial. Now, since this is the absolute value, I'm going to get rid of that first piece, and we're just going to have our, let's see, that would be a pi over 12. Because we had 13 pi over 12 minus pi, so that's going to leave us with 1 pi over 12, raised to the 2n plus 1 over 2n plus 1 factorial. Now, that needs to be less than 0.001. So at this point, I'm going to go over and I'm going to lean on technology again. And I'm going to start in y equals. And in y equals, I'm going to go ahead and type the left-hand side and the right-hand side. Let's see if it lets me move this out of the way. Here we go. Alright, I'm going to type the left-hand side and the right-hand side. So the left-hand side I put in y1, the right-hand side I put in y2. First thing I should notice is that I've got a factorial in there. So if I try and look at this from a graph perspective, we're not going to have a connected graph. Intersect features probably not going to work too well. We're going to run into some issues. So I'm going to look at this from a table perspective instead. So first thing I want to do is I want to make sure that I'm at a good spot on my table. So I'm going to go second, window. And I'm going to want to start my table at 1. And I'm going to want to take increments of 1. Because we're talking about the first term, the second term, the third term, the fourth term, and so on as we go through. Alright, we're trying to find that n value that satisfies this equation. Alright, so that would give me the n value where we officially, the n plus 1 term is a little bit less than 0.001. So if I go second graph, that takes me to the table. And we'll notice in the table that when I plug a 1 in for this n value, so when I'm at the first term of this, alright, I'm going to get a 0.003. So we're not small enough at that point yet. When I plug a 2 in, so when I'm at the second term, then the third term is 0.00005. Alright, and at that point, that is smaller than 0.001. So we're really looking for n values greater than 2. Alright, so if I have an n value greater than 2, alright, that's going to give me the value that works for us. So I look over to my answers and I say, okay, when is n going to be greater than or technically equal to? Because if I jump back to the calculator, notice when I was at 2, I was already under that. Alright, so n has to be greater than or equal to 2. So if I jump back to the 2, alright, 2 represents the term number. So the second term is right here. Now, in that second term, I've got to focus in on the degree, because that gives me the degree of the polynomial that gives us the sufficient level of error that we need. Alright, and the degree of the second term is third degree. That means that our proper answer for this one will be 3, which is choice A. Alright, another tricky one. Definitely got hung up on the right questions. These are tough ones for sure. Hope that was helpful. Thanks.